Hi, my name is Kevin Laube. Welcome to the brief 10 minutes presentation of what to expect of hardware metric predictors in neural architecture search. So our setting is multi-objective architecture search. That means we want to maximize, for example, accuracy and minimize, for example, latency. And of course, the question is, why should we predict metrics if we can just measure them? And there are many good reasons for that. For example, if we have a prediction method that is differentiable, then we can use gradient-based architecture search even if the metric itself, such as latency, is not differentiable. Also, predicting is usually faster and cheaper than measuring live. That means we can be faster than in our architecture search. We can decouple the search from the hardware. That means we can run the search, for example, in the cloud and scale it quite a lot without needing any more hardware. And also, if we have a predictor trained just once, then we can use it any number of times in parallel or subsequently, and don't have to measure live all over again. However, predictors are not perfect, and we'll see that in the following slides, where we show first off which predictors are best, and secondly, if we have predictors, then how does it affect architecture search? Okay, let's see which predictors are best. We ran an empirical study over quite a number of different metrics and devices here on Hardware NAS Bench, which is a cell-based search space. And you can see that we have a Kendall's Tower ranking, which is optimal if it's 1, because then we have a prediction that correlates exactly perfectly with on the test set with the ground truth. And you can see that depending on the training set size, our predictors are getting better. We can also see the horizontal line here, which is the lookup tables, a quite commonly used prediction method in architecture search. And we see that pretty much every data-driven predictor doesn't need all that many training samples to improve over it. On the right-hand side, you see the same data as on the left, except that it's centered on the average. That means it's good for comparing against each other. And we see that initially methods such as NOW or GCN are exceptionally well because they are using input encoding. That means they're just transforming how the architecture is represented. We also see that initially, for example, ridge regression is performing quite well, but soon, given a few hundred or 1,000 training samples, we see that MLPs and also tree-based models are improving over them. Secondly, we run the same experiments on TransNAS Bench, which is a macro search space. That means we consider layer by layer, and also the total number of layers in the network may change. And we see here that there is quite some difference. Simply, well, MLPs are performing much better than any other model. Also, lookup tables are performing better than before, but still there are no match for data-driven models. So the next part is, how does it affect architecture search? And well, on the left plot, you can see that predictors are not perfect. So even for some high ranking correlation of Kendall's Tau equals 0.7, you can see that they make quite some mistakes, and there is quite some deviation in there. On the right-hand plot, you see the same data as on the left, except as a histogram, and you can see that a lot of times the predictor is quite close to the ground truth with, well, around 0, but quite often it's also far away. And how does it matter? Well, consider the scenario. We have architecture search. We want to maximize accuracy and minimize latency. And well, you can see that 2 of these architectures are optimal. They have a perfect trade-off. And 2 others are not optimal, which are in the gray box. The goals are conflicting. That means usually when we maximize accuracy, we get a larger model, which has a higher latency. And the best models on the trade-off are the Pareto front and they are the Pareto set. And well, if we have perfect information as here, then it's not that hard to figure out which the best models are. However, in practice, as we could see before, our prediction methods are not quite perfect, and we may end up with some deviation on the ground truth. And that means we may make, well, mistakes simply because that's the data that we have. and we may end up selecting the wrong architectures, which results in this here. You can see one of the architectures we selected was in fact Pareto optimal. The arrow on the left points us to an architecture that we missed out on. We believed it was worse. And you can also see the one at the bottom that we selected, which is dominated even by another architecture that we did select. So it's suboptimal. Okay, next we will quantify this, both as a drop in accuracy on average and also lost hypervolume. So here's how we do it. On the left-hand side, you can see how we measure loss in accuracy. On the right-hand side, the result. And let's consider the red line first on the results. You can see that even for a quite good predictor, for example, Candice tau of 0.9, we can have a reduction in accuracy of almost 1.5%, which is of course terrible simply because by choosing a prediction method, we end up losing accuracy on the results. The green bar here is what we considered before. Even within our own selection, we may have some architectures that are suboptimal. And if we get rid of all of them, then we end up with the green line. And you can see the green line is already quite a lot better than the red one. For a good architecture, for a good prediction method, we have Candice tau of 0.9. And we can see that the green line only loses like 0.5 percentage points. How do we get the green line? Well, we need to get rid of all of the architectures that are in fact suboptimal. And that means we have to measure them. We need the ground truth information because our prediction already led us to the wrong results. The second thing that we consider is the drop in hypervolume. You can see the hypervolume is in a two-dimensional problem essentially the area under the curve with respect to some reference point here. That means if we want to maximize the area, then we get high accuracy and low latency, and that's exactly what you want. So on the right-hand side, you see high hypervolume is exactly what we want. And if we have a perfect prediction method as on the far left, and we have a lot of considered architectures like the entire search space, then we also get a maximum hypervolume. As we go further to the right, you can see that in fact hypervolume is being lost as long as we use worse prediction methods with decreasing Candice tau correlation. And also a second thing that is noteworthy here is if we consider fewer architectures in our search, then we may have never seen optimal architectures. And that means we also have reduced hypervolume simply because we never saw them and we could never pick them. We can see that there's a trade-off. If we consider more architectures, we're getting better. If we have a better quality of a prediction method, we're getting better. And this trade-off essentially means that we can consider more architectures with a faster method. That means by not choosing to measure in live, we are getting faster. We are losing out some optimality on the prediction method, but instead we can measure more architectures and we can still get better than before. So to conclude this presentation, here are some recommendations. So it is worth investing into a suitable prediction model. We found MLPs to work exceptionally well, especially on TransNAS bench. We do not recommend to use lookup tables. They have high variance depending on which data set you're using them on, and also actually not quite as good performance. They're very simple, but they're outperformed by other methods, even with only a few training samples. If you have only a few training samples, then we recommend using rich or even linear regression, which often works better than many sophisticated methods. And if you have a lot of training samples, as I said, MLPs or even tree-based models. We strongly recommend to validate your results if you used predictors to obtain them, because not all architecture that you do select will be optimal. There is still some deviation depending on how the quality of your predictor plays out in architecture search. And yes, it is generally beneficial to use inaccurate predictors if you can be faster and evaluate more candidates. Thank you for listening. If you have questions, then please have a look at our paper or visit us at the poster session. And the code and the results have been made available, so you can try your hand at it, reproduce it, and maybe continue this. Thanks.